Good morning. Thanks for waking up early for this. So my name is Norm Tubman. I'm at NASA Ames, and a lot of this work was done with also my colleagues at NASA Ames and a lot of other people, but I want to specifically give shout-outs to Antonius Albertus, who's been working with me on a lot of the material science parts of this, and Wayne Mullenix and Eric Gustafson, who've been working on a lot of the optimization stuff that you'll see in these slides. Just to give a feel, I'm not quite sure I'm in a session that's particularly well suited for me. So I'm more of an ab initio. So when I said complex materials, I was thinking more ab initio complex materials, but we do have some Kitiev models in here, so maybe this is okay. But just to introduce the sort of things that I'm interested in the ab initio field, this is a figure that shows where density functional theory calculations have been used over the last 20, 30 years. And when we think about running material science problems on quantum computers, we're always looking to run things that aren't really well described with density functional theory. And one thing I like about this plot is that a lot of the things that we think work well with DFT, and there's always exceptions, things like various energy comparisons and getting ground state structures and things like that. But getting complex ground states, like with magnetism or looking at bond breaking or things happening on surfaces, those are always harder problems that we think, DFT might do well, it might not do well, but we always are looking to have better tools. And these are the sorts of things which are also much less represented than some of the things that we really think DFT are quite useful for. So these are the sorts of things that I think are good targets for what we're looking when we're doing ab initio or trying to look at where ab initio calculations can run on quantum hardware. I'm going to tell you a little bit about this paper down here. About a year ago, we did a nice study, or I think a pretty nice extensive study of what the Hubbard model would look like with VQE with different ansatz that have been proposed in the literature. We did systems up to like 32 qubits. We did the MP ansatz, the EP ansatz, things like that. And then our next step was like, well, Hubbard models are great, but a lot of real materials can also be mapped down to Hubbard-like models, not quite a one-band model, but various extended Hubbard models. And we wanted to get into that. We wanted to start with some semi-easy materials that we could do benchmarking with, but also would have somewhat exotic ground states. So in this paper, we looked at this one-dimensional Hubbard model, which is calcium 2CO03. This is WTE2, which is hypothesized to be a excitonic insulator, and this is a strontium vanadium oxide 3, which is a perovskite system that has various interesting properties. One of the main results that we got out of this paper with our best VQE with various ansatz we're looking at in comparison to DMRG and the fidelity related to DMRG. And we did a lot of work to get these numbers. I think they're mostly recreatable with the strategies that we employed in the paper if you read the paper for detail. But there's a lot of things we had to invent or try out to get these numbers. And I just wanted to share one or two of the things that we looked at or were really pushing on in order to map these materials down to things that we could test out classically and start trying to understand how hard they'd really be to run on quantum hardware. So before I get into the two things that I'll really push on, I want to say that the workhorse of doing all this comes from having really good classical simulators. And in fact, one of the main algorithms I'm really going to push on is doing pre-optimization, warm starting, and any number of other things that you can do on classical hardware before you even think of taking one step of VQE on quantum hardware. For people who've seen my talks before, I've talked about these two papers probably very significantly in a lot of my previous APS talks. This paper in particular is an approximate circuit simulator. It is really tailored to looking at chemistry types of problems, but if you're willing to deal with approximations, you can really get circuit simulators that can test VQE, time evolution, and any number of other things from 64 to 128 qubits for chemistry types of problems. This is more of a tensor network approach. This is more of a chemistry selective CI approach, and we're looking at the Hubbard models and things like that with this. And just on our laptops, we could scale up to 32 qubits, maybe 48 qubits, and it really depends on the dimensionality of the problem, as you might imagine from dealing with something like that. But I really want to press on, I always do these in my talks, that having good classical circuit simulators allows you to explore a lot of things. And one aspect that we got out was a table like this where we could go through various molecules. Most of these are around 64 qubits when put on hardware, and we can compare against good classical methods, MP2, couple cluster, ASCII, and also the quantum circuits, UCC, with different parameterizations. Anyway, I won't spend too much time on that, but just to say we've expanded on these sorts of things in the last year to do adapt versions at very large scale. So I think this is probably the largest classical adapt calculation at 52 qubits. We can compare against other classical methods. So we're really refining our tools to push on classical simulation, how it can help with quantum, or doing VQE and other methods on quantum hardware. It looks like some of my figures just disappeared. Okay. Never mind. What I want to say, I want to show you one figure that sort of shows you why or what challenges we have in doing these pre-optimization techniques and really pushing on the classical side. And it's not barren plateaus. We have double precision numbers. When we do our optimizations, we can go to multi-precision if needed. Barren plateaus are not our biggest problem when doing these classical simulations, but I'll show you what is when we go to the next few slides. This slide I just want to push on. I'm going to show you some data for a square octagon Kitaev model. I usually show some hydrogen data, but this audience, it looked like the Kitaev model would be more relevant. Let me just get to it. We're going to be looking at VQE optimization. With this type of circuit, we're going to have multiple layers of this. So we have parameterized 1 2-qubit gates, or 1 qubit gates, and we have C0s for the entangling gates. We're going to look at 1 layer, 2 layer, 5 layers of these things up to 20, and we're going to look at what happens when you do VQE to get the ground state. And the main thing here, because we're doing this classically, and we don't really care about barren plateaus, we're going to be able to test a lot of starting configurations and really scan the potential energy landscape for different local minima. So this is kind of cool that this came after the previous talk. This is more of a brute force version of what you'd be getting into if you're to do the Kitaev model. And this is kind of one of the main slides of my talk that I want people to really understand. So what we have here on the x-axis is we do 100 simulations. We do 100 random starting points in our potential energy landscape, and this is just the index. So and we sort the things afterwards, so that's why it looks like there's a monotonicity to this, but these